To get things started, we know that the mining industry is facing incredible pressures, whether it's decarbonization, ESG, circularity, there's just a lot of pressure. So we're fortunate to have Paris Smalls here. He's the co-founder and CEO of Eden GeoPower, coming up from Boston. He's a PhD candidate in the MIT Who-I joint program. I'm not even going to ask what Who-I means. We can talk about that later. He co-founded Eden in 2017 and leads the development of the company's core electrical stimulation technology and go-to-market strategy. He's got a number of awards and accomplishments, including the NSF, 2 NSF awards. I'm not going to go over the acronyms, Paris, because I'll just stumble. And he's won Entrepreneurial Lead Awards, Entrepreneur Magazine's Young Millionaires 2020 edition, E&Y Entrepreneur Access Network 2021, and Forbes 30 Under 30. And what's really cool is Paris is still a student running a high-tech company and pitching to people and raising funding. It's really cool. Paris, the floor is yours.
All right, and it's WHOI, it's Woods Hole Oceanographic Institute. Yeah. All right, so I'll just press this button, I'll go. Okay, so we're Eden, and we also break rocks, and I'll tell you a little bit more about how we do it. So in order for you to recover any natural resources, you need to have permeability. We're focused particularly on permeability on the subsurface for different kind of market verticals, going from geothermal. If you want to sequester CO2 in the ground, you're going to need permeability. Of course, oil and gas, think hydraulic fracturing, right? And mining is a new one for us that we're going to be talking about a little bit more. Okay, so what we do is essentially we utilize very, very high voltage electricity. Think hundreds of thousands, megavolts of potential difference between 2 different points across a geologic medium. So this is a example schematic of a process called electrolinking, where if you can jack up the voltage high enough, you have a front that propagates that becomes very conductive, and you can keep getting these fractal patterns to go from point A to point B. What's really unique about the potential for this is that you can have a lot more control on where you create fractures. The parallel would be hydraulic fracturing, to where you don't have control. It just comes out from a sphere, but with this process, you can orient your electrodes in a way that would allow you to be able to create fractures independent of the in-situ stress state, which is very important when you're trying to maximize the reservoir contact area that you have. So a brief overview of how this will work in in-situ mining is that we will combine our technology with fluid injection to be able to create a very highly conductive artificial reservoir. So we're going to be injecting fluids. That fluid is proprietary, something that we're working on. It's going to have properties that will allow us to be able to geophysically image it, so we can then figure out where we want to drill the next wells, put electrodes into each well, start passing a lot of current into the reservoir, and then repeat a few processes until we have the amount of fractures and permeability that we want. And there's also the potential, depending on the reservoir, to be able to inject CO2. CO2 mineralizes, and that's something that we're going to be looking forward to in the future. So it's been a really great year for us. In the past 12 months, we've received over $8 million in non-dilutive funding from the U.S. Department of Energy. I'm the principal investigator for this application here, for the geothermal application. And we're working with Idaho National Laboratory and a couple other universities, including Colorado School of Mines, for the mining application. Well, again, essentially our thesis is, how do we drill wells into rock bodies? How do we electrically stimulate these bodies? And how do we better control the fracturing process? So where we are in the technology development right now is that we're in the middle of coming out of the laboratory, and then we're going to the field this year. So this is a picture of our laboratory setup. Essentially what we do is we take a rock core, we put it in a triaxial cell so we can be able to change the differential stress state, and then we're able to inject fluids on the ends of the core And then we have the rock core. On both ends, we have an electrode. Some of the things that we've been seeing that's been very interesting is that when you start passing high current into a rock, a water-saturated rock, the rock begins to increase in pore pressure very rapidly. So we started at an initial state of 0.2 megapascal, we went up to 4 megapascal. And because we had differential stresses on this rock, it actually caused shear failure. So when you're in deep in the reservoir, you're going to have different kind of pressures acting on it. So you don't necessarily have to completely break the rock. It can fail under the stress state of the reservoir, which is very interesting. And so we're going to be investigating this a lot more, different kind of stress states, different kind of materials. In this case, we did various sandstone. We haven't started testing on ore-rich rocks yet because we haven't had access to those kind of rocks. But I think that's going to be a very natural next step for us. So where we are, and one reason why we're here is that we are raising capital. We're doing a $10 million seed round. We have $6.4 million committed to date, signed a term sheet about mid-February. And we need to start taking things from the laboratory into the field. And so we have 3 different opportunities that we're going to be looking at in the next 24 months, spanning across essentially 3 different kind of geologic reservoirs. The first one is going to be an unconventional petroleum reservoir. We have sponsorship from a company in Oman, and my team is flying to Oman next week, where we have a lot of big power devices that we're going to be taking there. We designed some new electrodes. We're going to be putting a lot of electricity into wells, spaced around 300 meters apart in that case. What's really cool about the mining application and also for CO2 injection applications is that the wells can be a lot closer, which matters a lot for the success of our technology. And we're doing another pilot where we're also in Oman with a company called 4401. What they have are very ultramafic kind of rocks that react really well with CO2, but they have very low permeability. So what we're going to be doing is taking our technology, picking it up to our electric stimulation equipment on the surface, and we're going to be super shocking these reservoirs into the rock fields, and we're going to be testing permeability before and after. And then the last thing we're working in is the Sanford Underground Research Facility in North Dakota. This is an abandoned gold mine, and we're taking over a drift at the 4,100 feet level. What's really unique about this opportunity is that we're going to be able to test our technology with wells drilled only 100 meters deep, but yet the overburden pressure is going to be 30 megapascals because we're going to be deep in these tunnels. And so we have a lot of opportunities right now to take the technology to the field, different kind of geologic environments, and keep moving that TRL down towards none. And with that, I'll end my presentation and take any questions from the panel. Thank you.
I can start. No one, great presentation, very exciting. I think any way we can liberate or crush rocks more efficiently is definitely welcome. In terms of the amount of energy, and so some of our mines, we struggle with the grid to get the level of energy that we need to sometimes implement battery equipment. And what will be needed, not just from your technology, but from the surrounding infrastructure in some of these remote communities to allow this to work?
So the energy question is a great one. And of course, it's very natural that we did an energy budget analysis. There are 2 ways in which you can pass electricity into these reservoirs. The first one would be with the continuous AC/DC, and those power supplies scale to about 5 kilowatt currently. You can get that commercially available. And what we've estimated is that we'll run that for up to 2 weeks. So energy budget would be 24 hours times, 14 days times, whatever kilowatt you end up doing. In the field in Oman, we're doing that pilot, we're doing 500 kilowatt. And we're only running that for 4 days, but that's just simply for the pilot. So you can think on the order of, let's say, roughly 100 megawatt hours as an energy budget to be able to create a nice zone of fractures between well space, let's say 50 meters. That'd be a good number to have. And that's for the continuous energy input. You can really significantly, by a couple orders of magnitude, decrease the energy input by going from continuous energy to pulse power. Because what you would do is store the energy into these capacitive banks and you would discharge a lot. at a time, but each discharge you do would be on the order of 0.01 kilowatt hours. And you have to store it, you have to wait a couple seconds and then release. And so you might only consume, in that case, over the entire stimulation period, a couple hundred kilowatt hours. So what we need to do in order to decrease overall energy consumption is move from continuous energy to post energy. And we are signing agreements now with a developer of post power equipment that will have all the access to IP for to start developing some of these power devices.
My question was actually similar, exactly talking about the energy, the budget and the load, because I was also thinking about the remote, mining as well, where already the source of power is already an issue, which you said was really interesting as well. So this is just an add-on to what Luke was saying, but getting that energy storage piece alongside it, I think that would be really compelling. But then again, it's a larger question around what sort of balance of plant infrastructure is needed, alongside this, alongside the technology itself.
Yeah, so for the pilot that we're doing next week in Oman, we actually it's also off-grid. And what they have is a 1 megawatt diesel generator. And we're connecting that to our 500 kilowatt power device, and that's what's powering the operation. So as we scale, we need more power, and if we're off-grid, but it'll be essentially how do they currently get power in these locations, which is likely be burning diesel.
One of the things that we are faced with in oil and gas, for example, is the fracking uproar, and the kinds of things that are being demonstrated against in all parts of the world, including parts of the U.S. And that, I'll throw something out there. Let's say the concept of aquifer destruction. If, for example, misguided energy inputs sort of compromise typical trap rocks for aquifers or that kind of thing, where you break those trap rocks and suddenly you've got the aquifer escaping into the trap rocks. Like, do you see an ESG pushback against this kind of thing?
I think we have a very strong argument for why you would want to do this, as opposed to just purely hydraulic fracturing. And this is the slide. I kind of tried to allude to this a little bit earlier. One of the benefits of what we're doing is that we are able to control by purposely designing where we're going to put the electrodes, where the fractures would occur. We know generally speaking that the fractures are going to occur in some kind of pathway between the electrodes. So therefore, as opposed to hydraulic fracturing, where you're completely dependent on the stress state, and if you don't have a really well-characterized stress state, the fractures could go and leak into your aquifer, and that has been an issue. With this process, we're able to create the fractures where we want to create the fractures, and therefore mitigate those concerns. And also by introducing these electric pulses and this high voltage into the system, we are decreasing the amount of high pressure fluids and water that has to be injected into the reservoir to create the fracture. So therefore you reduce dramatically some of the environmental issues associated with seismicity and contamination with all the fluids that go in with traditional hydraulic fracturing. So there's a very strong ESG argument.
Okay, good. Thank you for that.
Quick question on the technology. So on this great slide you have, can you talk about the actual timeline, the time that you have? I just want to understand the performance or the efficiency of the technology. And then one additional question to that is how do you manage, for example, the variation of your rock? How would that change the performance of your technology?
Yeah, so for the timing, this process that we're looking at here, it depends on the spacing, of course, of the electrodes. It should be on the order of a couple of seconds to a couple of minutes. And it also depends on the applied voltage that you have. So we're going to be studying that a little bit better, and then looking at how it works with different kind of materials. So there's a lot of different variables that go into that. Regarding rock heterogeneity, that's something that we're going to need to study in the field, because usually when you get cores in the laboratory, they're just like one. You have just a sandstone or a granite or just whatever it might be. But in the field, you're right. You're going to have likely, as you transition, different kind of geologic bodies that you're going to be going through, and we're going to get the data points on that once we start field testing. But right now, we don't have a good feel for what that transition along geologic bodies as you pass the current is going to have on the technology.
And then one more question on the product roadmap or technology roadmap timeline. I know that somewhere that you're raising seed round at the moment. Can you talk about, what's the milestone for your next funding round, and then how that align with your technology development?
Yeah, so within the next 2 years, we should have a lot of data points in the field, and we want to use that to catalyze our Series A. So I think we'll be targeting like a $40 to $50 million Series A, and we have a lot of opportunities now because we have gotten sponsorship from the U.S. Department of Energy that they have built-in internal funds for next step. For example, RPE, what was it called? RPE Scale Up has a $20 million per project that they put into, and it's not diluted, they put into you to go and start commercialization. So within the next 2 years, once we get some of this demonstration work, we'll be able to tap into that non-dilutive money as well. So it'll help us accelerate the technology development.
On that note, it sounds like we're talking about at least $50-60 million of investment before commercialization. Can you comment on what the business model looks like post commercialization and what sort of indications you have from folks that are already doing pilots?
Yes. So I'll put these four here for a reason. What's really unique about our technology, while we are here at a mining conference that has applications across the spectrum of reservoirs where you need to increase permeability. So the way that we're looking at doing this right now, and it's where we are in the moment, is that we're essentially like a service provider, think like a Schlumberger or a company that goes and, you call us, we break the rocks for you, and we're a little bit more agnostic as opposed to, what industry is going to be for. So of course there's, hydraulic fracturing is a really big one. So we can help mitigate some of that with our technology. That's going to be a really big market for us. There's going to be a lot more capital being put in the CO2 sequestration. Particularly, we're really good with mineralization, where you need to actually create these pathways, and then it's going to mineralize and lower permeability, so you got to keep fracturing it. And for geothermal, which has been really hot lately, in order for geothermal to scale, you need to have enhanced geothermal systems, which is when you need to artificially create these fractures in the reservoir. And we've been funded a lot by the government to work on this as well. So our business model, as we start to commercialize, is going to be, how do we take this technology and fracture it across the geothermal, mining, petroleum, and CO2 sequestration industries in the short term. In the long term, once we're able to access a lot more capital, what I think I want to do is start investing in the underlying resource itself. So if we're increasing so much value in a mine, then can we get some ownership of that mine, or some kind of ownership of the asset itself, because we're unlocking it essentially. And I think that's what we're going to move towards as the company gets bigger.
Awesome, thank you.